very quiet class this morning. All right, if you have not already clicked in your answer to this, I want you to do this without doing any real calculations, just estimating, eyeballing, getting a feel for it, all right? So I'm going to give you guys about 45 seconds. Try to think about what you would want to put as your answer, and then talk to the person next to you if you haven't already done so, or someone you haven't talked to about it. See which of these answers you think would be reasonable. All right. Some people could argue that this is, if you had a medicinal chemist in here and had him look at all these questions, someone who dealt with, or any professional chemist dealt with scale all the time with chemistry stuff, they would think that this was a super easy question. Like, why are we even asking this? But I think what this shows is that it's really hard to picture how big molecules are and how big something that you see in everyday life is and how that relates to all the numbers we have in class. So this is a question that I really want you to be able to answer by the end of this semester, today. Because to me this goes beyond crunching numbers. This goes beyond plugging things into equations. So I want to hear from a couple different people in this class how we might think about this problem and try to come to an answer with as little information as we have, right? There's not very much information here. Sam?
I was thinking D. I was thinking of Avogadro's number, and I think it's 10 to 20 to 30, something like that. So it's in that range.
Okay, so why Avogadro's number? What about it?
It's like how many molecules there are per something per mole.
Yes, that's how many things there are in a mole.
So it just fit in that range. So that's thinking about.
Okay, so
one mole.
Usually when I give this, I typically give exact numbers, and the mole is one of them. And a lot of people choose the mole just because it's a familiar number. So we need to think about what that means. Joey, do you want to elaborate on it? Or
I was thinking what he said also, but don't you have to convert it from grams to milligrams because they don't. You don't get a gram pill.
yeah, right. How big is a pill? Can you visualize a pill of Advil?
Yeah, milligrams. It's only milligrams.
Okay, so they're usually about 200 milligrams, 300 milligrams, somewhere in that ballpark. You don't need to know that exact number. So let's go off of what Sam said. Oh, you want to? Sorry.
Well, I was saying do what he said, where it's 10 to the 23rd or whatever. Then you also got to make that a little bit smaller. So you add to it. I don't know. I felt like 27 was just too big a number.
Okay.
But the Advil pill, if you think about it, that's not 200 milligrams of Advil straight. It's something else with it. Other compound. It's not just ibuprofen.
Okay. So does that mean
There's
that
sugars,
it would be?
there's salts.
Does that mean it would be bigger or smaller?
So that would make the pill the size it is that we take.
Yeah. So if you were to go weigh an Advil pill, it probably weighs more than 200 milligrams. The 200 milligrams is how much of the active ingredient you take. They have to disclose that so you know the dose you're taking.
Right.
And so it probably weighs 400 milligrams because it does have sugar, like a really nice sugar coating on it, and it might have some other formulation. If it's extended release, it has additional things added to it as well. So if we think about this, if we had a mole of Advil, how much would that pill weigh?
150 grams.
Do you want to take a 150 gram pill of Advil?
No.
Can you picture how big that is? You guys have used the scales in labs, so I know grams aren't very commonly used in everyday life, but you've been in the lab for a whole semester now at least. So that means that if you have a mole of Advil, it's going to be a chunk that's bigger than your hand.
It's also, if my grams to ounces is correct, it's about half a pound of this stuff.
Yeah, it's a lot. Okay, so what I want you doing from there is you factor. Okay, so how much smaller is it? Is it 10 times smaller? Is it 100 times smaller? Is it 1,000 times smaller? Right, each one of those is an order of magnitude. So what do you guys think? Talk to your neighbor and try to click in one more time what you think your answer would be. Couple more seconds. Click on your final response. All right, so we have a distribution between B, C, and D now. If we knew the exact weight of the pill, we could be a bit more specific. But if Avogadro's number is, let me do this written out, 6.022 times 10 to the 23rd. If that's 150 grams, if we knew the pill was 200 milligrams, then how much smaller is that? So 10 times, 100, 1,000, 10,000? So it's about 100 times smaller, right? So 150, if we move the decimal 3 times, sorry, it's 1,000 times smaller. So 10 to the third smaller. So that would give us 6.022 times 10 to the 20th. Ballpark. So it'd be really close to the border between these two. And that's if you knew the size of the pill. But I think if you go home and you look in your medicine cabinet at all the different pills, you're never going to see a pill bigger than 1 gram. It's like a horse pill. That's something that you would not want to take. Usually suppositories are that big.
Wouldn't it be closer to 10 to the second to 10 to the third?
So if we make it 1,000 times smaller, it'd be 150 milligrams. So it's going to be a little bit bigger than that.
Oh, yeah.
So it's going to be pretty close.
Wrong thing.
Right? So this is the kind of thing I want you guys thinking about. I want you thinking about if we look at this pencil, how many grams does it weigh? And then how many atoms would be in it? If we think about a drop of rain, how many water molecules would be in that? Like, I want you to have a ballpark, right? So either way we look, it's 10 to the 20th, 10 to the 21st. So these first two answers are completely irrelevant and are not possible, right? This is
That's like
10 million
scale.
So 10 million molecules sounds like a lot, but it doesn't weigh much at all. This one goes up to 10 to the 14th is 100 billion? 100 trillion, sorry. Still not very much in terms of molecules. All right, and then these ones are more than a mole, which means it's more than 150 grams, which means it's going to be excessive. So this kind of like logic, thinking about relative scale, is going to be really important. For me, I will have a test similar to this on the exam where you have to think about scale. It's not going to be this question, obviously, but it's going to be give me the order of magnitude of how many there are or how much something would weigh without giving you enough information to have all the pieces together. If you have a question on that during the exam, you can raise your hand and ask me. I may or may not be able to answer your questions. All right, so a couple logistic things before we get into the rest of our review material in class today. Post-survey is out. I think we have 28 responses, which means we probably have about 25 to 30 left. Remember, that does count as a post-quiz. So that post-survey, I'll send the link out again today if you have not yet done it. It's a Google form. How long does it take? 20 to 30 minutes, is that fair? Okay. And remember, I can see the results, so if you don't actually go through it and put in reasonable answers, then I will be hard-pressed to give you credit for something you did not actually do. Then we have exam review sessions. I have one today from 1 to 3 o'clock. One tomorrow. We decided 10 to 12 was the best time. And then I will set some up for later this week. When's our next? Is the 10th Monday?
Yeah, we're final on the 5th.
So I was just trying to figure out if it was Monday or Tuesday. So then I'll have probably 2 review sessions, one on Thursday, one on Friday. That way, hopefully, you're able to make one of those if you get your score back on Wednesday and want to take the second final. Your best score of the 2 counts.
Oh, so it comes back that fast?
It's all multiple choice, so it's Scantron, which means as soon as I get the scores back, I will post your percentage. What you will not know is how that affects your other grades. It's going to take me a while to figure out how to extrapolate. Did you master molecular shape? Hence, I'm going to give you credit on exam 2 for molecular shape, right? That's going to take me a while to do. I can post your raw score for exam 4. That's easy for me to do. So I'll post your ACS final score on Blackboard. You should see that by the end of the day on Wednesday. From that, you can decide whether you want to go ahead and take the second optional final exam. If you do not take the first final, you cannot take the second final. Let's be very clear on that. Yes?
Would you consider giving us credit for
You'll earn
topics
half the
we haven't
percentage.
gone over?
Say again?
For subjects we haven't gone over, the ACS, like electrochemistry?
So for the things that you have not done, so electrochemistry is not going to be on our exam. Our exam is first semester Gen Chem only. So some of the stuff you might be talking about, kinetics, equilibrium, electrochem, those kinds of things, or you might have seen the Olympiad chemistry. Those include additional topics. Our final exam includes everything that we've done, plus quantum, and there's like 1 or 2 other questions that use some terminology that we haven't used. So I will remove the questions that on the topics that we have not done from your grade in the final exam, but I need to report how you do on those. So you have to answer every question. There's no penalty for answering questions. Your grade will come from the things that we have done in class. Trixie?
So on the ACS, we will have electrochemistry on?
No, there's no electrochemistry in that. There is redox, but there's not electrochemistry, which is voltaic cells. So just a couple notes about that ACS final. I wanted to get on the same page. Remember, no graphing calculator. As you practice for the final, do your calculations on a regular calculator that you're going to use during the exam. It sucks. I think our first exam in here, even I saw some people pull out a calculator, open the packaging, and start using it. That becomes very challenging sometimes to figure out scientific notation. So let's not try to do that. Remember, there is no note card. The things you will be given on the final exam, though, on the ACS final, this is literally a picture from the cover sheet that has a list of abbreviations and some constants. So your gas constant, it has Avogadro's number, it has Planck's constant, speed of light, and the conversion between Celsius and Kelvin. Yes?
Do we need to know solubility rules, or are we going to be given that?
I don't remember there being... I need to go back and look through the test. Whether they ask you about solubility specifically. I will. On my final, I'll give you the solubility chart. I'll give you the electronegativity table. But this one does not. So can you post that to Blackboard discussions, and I will reply there? Thank you. As far as test taking strategy, I just wanted to mention 1 or 2 things on the ACS final, because I think you guys do have the potential to crush it. If you do come up to a question that you don't think you can answer quickly, put a mark by it, come back to it. This test does have 70 questions. There are a lot of questions on this test. If you're going to finish it in time, make sure to get the low-hanging fruit first. Always complete the questions you know how to do first. One big mistake you could do, though, is not bubbling in your answers as you go, question by question. 70 questions is a lot to bubble in the end. Don't do that. So make sure that you work through the problem, you get your answer, you bubble the answer in for the right question number, and then move on to the next one, or skip it, make a star, come back to that. You don't want to spend time in the end trying to bubble in answers. And actually, I think you can't even write on the exam itself, so we'll be giving you scratch paper. So you'll take all your notes and do all your work on that, because the exam, the physical exam, is used over and over again. We buy the copy once, and then we use it for multiple semesters. So it is a protected exam. It is a physical piece of paper that you're not allowed to write on. Any questions about the exam?
So you said we could bring a piece of paper.
I will bring blank paper. You will not be able to use your own paper. You can't use your own periodic table card. You can't have any of your own stuff aside from pencil, calculator. I think that's it. Yeah.
That little business card you gave out, like.
No, you'll have a. There's this and there's a periodic table right below it. So you will have a periodic table. But the idea is you can't bring any of your own stuff in, because if you're taking notes on trends on that little card, you can't have that during the exam. Same with my final. That's why I provide you with the periodic table. Plus there's obviously some around the room.
So we can't like pull it off. It's just on the front, so we would have to keep flipping to see it.
True. I'll see if I can find a stack of periodic tables I could provide. There might actually be a pile over here somewhere from one of the previous exams. If I can find that, I'll provide those additional.
Are they gonna cover those?
No. The idea is not to have multiple periodic table cards. The idea is that you cannot bring your own material and have it sitting in front of you during the exam. It's a protected, standardized exam across the nation, so it needs to be done the same way. So, yeah, Joe. December 5th, 10:30 to 12:30. Correct.
Is it in a different room?
I actually don't know where we find the room. I hope it's in here.
It's in here.
You've done it before, in the same room?
4 years ago, man.
I will find that out today as well. Can someone volunteer to send me an email to look up the room location and send that to you guys?
It's supposed to be here according to the.
It is.
According to the final schedule, they make it to where this is your room whenever you taught this class, so we're supposed to be here.
Sweet. Okay, final exam as far as we know is here. If anything is different, I will notify you through Blackboard announcements. All right. The great thing about this is that you guys have 2 chances. So if you're really unhappy with your score in the ACS final exam, you have my final on December 10th. And Joey was going to contact me about that, and then I don't know if anyone else.
About what?
The final exam on the 10th?
Yeah, we gotta see how we do on first.
Yeah, but scheduling has to happen sooner than that, so please contact me if you are unable to make the December 10th date and time, because I will bunch everyone together that's not taking it that time, and you guys will take it at a separate time. All right, you up for some review?
Did you put a timer up whenever we get the
During the exam? Yes. Remind me during the exam, and maybe I'll try to plug something in and have it up on the screen so it shows you how much time is left. All right, so let's go back, and I have a whole bunch of questions because there was so many people that posted a Blackboard about what you guys wanted to work on today. I just picked some topics, and some of the ones that the person posted are here, okay? So we want to think about some electricity here. I want you guys to go ahead and start working some of these problems. We're going to try to work through these as quick as we can because we have about 20 questions we're trying to get through. And these are fairly similar to what you would see on the ACS. So we're going to go to about 1.5 minutes, 2 minutes at the absolute most on this question. We're getting close to 1.5 minutes. Raise your hand if you're going to take a very long time because you haven't studied this yet, maybe. That will tell me how much time we spend waiting for people, okay? So let's go to 2 minutes. Try to get as much as you can of the process written down. And then we're going to talk through it, but make a star next to this is something you need to go back and study if you don't feel very confident in this right away. All right, 2 minutes is up. First step, let's popcorn this. Let's have different people volunteer. First step, what would you do to solve this problem? Kayla. Okay, we can balance it. What needs to be balanced? So I would argue that you could actually do this the other way around too. So you could balance it normal, and that would probably be fine. Did anyone balance it the other way? What do you mean? Did you split it into half reactions first and then balance?
No.
Okay, so the first thing you do is what Kayla said to me earlier when I walked around. She said, is this a redox reaction? Right? So you need to identify the type of reaction first. When we have a redox reaction, what do we typically do? We find oxidation numbers, we break it into half reactions, and then we balance the equations and we recombine them. So if we're going to do that, if we're going to assign oxidation numbers, could we simplify our life a little bit first? What are we going to do to simplify? So let's write the net ionic equation. That seems like a really good idea. So go ahead and take 1 second if you haven't already. Write the net ionic equation. Don't worry about balancing it yet. So Matt, do you notice any spectator ions?
Yes, the sulfate is remain aqueous.
So sulfate, SO42 minus. It's aqueous on both sides. So we assume that does not react. So then what's on the left side of this equation?
3 iron, 2 plus, plus Cu solid.
And on the right side?
And that's going to become iron solid and Cu.
Okay, so we don't have anything balanced yet. It's kind of this weird thing. I kind of overrode Matt when he started balancing them before we did this. Right, so what I want to point out is that this becomes a lot easier when we get rid of the spectator ions, because now we see that we have iron 2 plus and copper solid going to iron solid and copper 3 plus. What are the oxidation numbers of all of these different elements? Sarah?
So, copper solid and iron solid is 0.
So our oxidation number of any solid is 0.
And iron aqueous would be 2.
2 plus. We're always going to say positive or negative, and then copper.
And then copper would be 3.
Okay, so if it's an ion, the oxidation number is the same as the formal charge. So what's being oxidized? What's being reduced? Can we identify that? Make a note on your paper. What is being oxidized? What is being reduced?
Iron's being reduced and copper's being oxidized.
Say again? Sorry.
Iron's being reduced and copper's being oxidized.
Okay. So Leo goes Gur, losing electrons, oxidation. Copper starts with all of its valence electrons, ends up with 3 less per copper. So that means it's losing electrons, becomes more positive, has fewer negatives. Our iron 2 plus is gaining electrons and is being reduced. So then we're at the half reactions. So go ahead and write the oxidation and the reduction half reaction, balance those. Go ahead. Okay, so we wrote out what's being oxidized, what's being reduced. What am I missing in these two equations? Let's start off with the oxidation half reaction. Can I get a new volunteer? What am I missing in that half reaction? What do I need to add and where? Amber? Okay, and which side do we add electrons on the oxidation half reaction? How do you know that?
Because you don't write subtractions in these sort of reactions.
Great, you can't subtract out electrons. They're always being added.
And the left side, the charge is 0, and the right side is charge plus 3, and you want to get it to be 0 as well.
Great, so both sides have to have the same charge. Doesn't matter what the charge is, they're both going to be the same. So we have to add electrons to one of the sides to make both of the sides have the same charge. So on the right side, the way it's written right now, how many electrons would we need to add to the right side? 3 electrons. But we have this 2 up here. So let's include that 2 again. So that would mean we need 2 copper solids, gives 2 copper 3 pluses. And how many electrons on the right side? 6. So we have 2 3 pluses. That's 6 plus. We have 6 negatives. That's 0. All right, does someone want to tell me what we need to do for the second reaction then to make sure that that half reaction is balanced? Reduction? Ruby?
Add 2 electrons to the left side,
Why?
because there's a positive 2 charge, and then the 2 electrons will cancel that out to make it 0 as no charge.
Okay, so one important thing to note is that this just happens to be that we're trying to get to 0, but whatever the formal charge would be on the right side, that's what we're trying to get to on the opposite side. So we always add electrons to make them the same. This one happens that both of what we're trying to get to is 0. So we need 2 electrons for every iron 2 plus to get iron 2 plus to become iron 0. That's what this is saying. If we said this as a sentence, in order for copper solid to become copper 3 plus, every one of those needs to give up to release 3 electrons. And it's happening twice. Okay, so are we done? Do we combine these again and then we're back to our balanced reaction? So what are we missing? What's the main factor in balancing the half reactions? We have to balance the electrons. Because in order for copper to give up 6 electrons, it can't be giving those to iron that only takes 2, right? So somehow, however many electrons are gained have to be the same as those that are lost, because this is an exchange process. You never hear of a reduction reaction in isolation by itself. It's always redox. Redox means one is giving up electrons to something else. That other thing is accepting those electrons. So how do we make sure that the number of electrons given up are the same as the number of electrons that are accepted? Trey?
You need to balance the second half.
How do we balance that? What do you mean?
Well, on the product side, you have 3 sulfates, whereas on the other side, you only have a single one present, so you would need to make sure that
So careful, you're focusing on the spectator ion. And so we're not worried about the spectator ion. We're worried about how many electrons are transferred. So I agree we need to balance it, but how do we do that thinking just about the electrons?
Multiply the bottom reaction by 3.
If we multiply the bottom reaction by 3, then we say that, well, this iron 2 plus has to happen 3 times to gain 6 electrons to make this reaction go 2 times. So that would mean then that we have 6 electrons, 3 iron 2 pluses yields 3 iron solids. If we add those all together now, we get our balanced equation. And now we can prove that to ourselves is if we write everything from the left side together, everything on the right side together, then we see that we have 6 electrons on both sides. That tells us that that equation is balanced. If we want to go back and write out the original equation, we can do that, but this question doesn't ask you to tell us how many sulfates are part of this equation. What is this question asking for? Well, how would we answer this question? Troy?
It's just asking for the number of electrons transferred, so it would be 6.
Great. So the number of electrons transferred is 6. Don't get confused and say 12. If I'm giving him $4, it's not $8 it's exchanged because I give him 4 and he accepts 4, right? That doesn't make it 8. So $4 are exchanged. That would be it. Here, 6 electrons are being accepted by iron 2+. 6 electrons are being given away. Those same 6 electrons are being given away by copper. That's for every 3 iron 2+s that go through this reaction. Okay, is this something you guys need to work on? Room is super quiet. So if you guys don't know how to find the number of electrons that are transferred, I would say work on that and show me how the process goes forward. Questions? That took a lot longer than I was expecting. All right, we have exam review session today and tomorrow. We can work on this there if you're still uncomfortable with that. All right, so now let's do another thing that I'm sure you guys are going to do very quickly. Which one of these 3 has the most energy? We're describing 3 different photons. Photon 1, photon 2, photon 3. Which one of them has the highest energy? All right, we're going to do 1 minute and 30 on this as well.
Yeah.
Okay. Getting close to 1 minute 30. We're at 1 minute 30. Rate your confidence that you know how to do this, even if you didn't have time to do it. Thumbs up, you're comfortable with it. Thumbs down, I don't remember where to start solving this kind of a problem. All right. We have our final exam in 2 days. So quantum was kind of a big part of what we did. This was part of the calculations. So how do we go about solving this kind of a problem? Josh? Which equation is really important to remember? Ruby?
HC over.
And the other version of that is H nu. So remember, this nu is frequency, wavelength, energy. They're all related to each other. They're all different ways of describing a photon. So if we have those equations, could you solve this problem? What are you going to do with those equations? Okay, let's use non-plug-in terminology. What would, so we would put them all into the same unit, right? Maybe you want to put all of them in the form of energy. So then you convert frequency to energy, you convert wavelength to energy. Maybe you want to put them all in frequency. What is hertz? What is that unit if we unpack Hz? It's 1 over seconds. Planck's constant? If you notice, units to Planck's constant is joules times seconds. So we should be able to work through this. All right. Calculation itself, you guys can figure out. We're not going to spend class time on that. All right. We only have a handful of answers, and you guys are all over the place. So I'm going to let you guys work on that on your own. All right. I'm just trying to give you guys a feel for what you need to be able to do for the final exam. And I think this is one where I don't need to spend class time working through the calculations. All right. Let's go ahead and talk about some atomic trends. Which of the following elements has the largest effective nuclear charge, Z effective, on its valence electrons? Take 60 seconds. Talk to your neighbor. Try to figure out what we're talking about. All right, submit a selection. All right. I could ask, so this might be terminology that you're not super comfortable with. I think your book probably had this in it. Is that true? Effective nuclear charge? Let me ask this question another way. Which one of these has the largest pull on the valence electrons, pulling them closest to the nucleus?
What are you asking like that?
Because ACS doesn't. So this is the terminology that American Chemical Society uses on their final exam. All it's saying is which of the valence electrons feel the most pull from the nuclear protons. How do we look at these and determine which one of them have the strongest pull from the nuclear protons?
Argon.
There you go. But it's a noble gas.
So you said argon. Why argon? Yeah.
Because it has a full octet, so that means that they're close together.
Okay, so we remember that if we have a full octet, we're furthest to the right of the periodic table. Atomic trends, our smallest is all the way to the right. Can you go back and explain why that is? Why is it when we go to the next element past argon, potassium, the atomic radius is now huge compared to argon? You want to try? Right? Go ahead, Josh.
Isn't it because we go up another shell, right?
So now we have one electron in a new shell, and the effective pull of the nucleus is shielded by the electron configuration of argon. Right? If we write the condensed electron configuration for potassium, it's argon in brackets, and then one lonely electron on the outside. What that's telling us is that argon's electrons are actually shielding that nuclear charge. That effective charge is almost zero. It's almost like it's only feeling one proton for that one electron that's outside of argon's electron configuration. So the effective nuclear charge, Z effective, is how much is the valence electrons, how much are those feeling? Because all the non-valence electrons are kind of shielding the protons. You guys feel how this works? So let's go ahead. So this one, I agree, it would be argon. What about this set here, the next set that we have? Which has the largest effective nuclear charge out of these?
What was the other question? Was it the smallest? The one before this.
It was the largest effective nuclear charge for both of them. A couple more seconds. And closing out. All right, so majority of you guys are answering lithium. Why would we answer lithium? Has the highest or the largest effective nuclear charge? Don? That's the smallest atomic radius. We know that those electrons are being pulled in the closest, regardless of the fact that all of them essentially have one proton that they're feeling because they're one pass noble gas configuration. It's going to be closer to the nucleus. So the effective charge, the effective pull on that's going to be slightly greater.
They go up by a shell each time.
Yep. All right, now let's do a little more difficult one. Which one of these has the largest effective nuclear charge? And I think you do have these on your worksheet, right?
Yeah.
Couple more seconds. All right, closing out. A vast majority answered bromine. How do we know? We have so many different elements. They're not in the same period or the same group, so how do we answer that? Jackson?
Well, I think we can all say we can rule out A because it's further to the left, it's the furthest to the left, and it's the furthest down. So it has literally everything going against it.
Okay, so big picture then. How do we pick from the remaining ones? Very concisely.
And then you have potassium, and then germanium is to the right, and then bromine is even further to the right.
So the big thing is we look, where is everything on the periodic table? It's all about the trends of the periodic table. So further to the right we go, especially in one period, the higher the effective nuclear charge is going to be, and the other one, cesium, is below all those. So I agree with the majority of the class, saying that bromine is going to have by far the largest effective nuclear charge. All right, you guys feel pretty comfortable with that? And you're able to say which one has the largest atomic radius using some of the similar terminology. That's something you guys could do. All right. Let's go through some more basic stuff. Let's go all the way back to the first couple weeks of class. 7 minutes left of class. We're going to try to get as many of these questions as we can. Go. Another 10 seconds. Closing out. All right, so what that tells me is those who took their time and answered comfortably know how to answer this question. Those that I just rushed, you guys might just want to be a little more careful with reading the question. What is an isotope? What's different about two isotopes? We have a lot of quiet people in here today. They're just letting everyone else answer. Yeah. Same number of protons, different number of neutrons. Exactly. They are the same element. They just have a different number of neutrons. So we could tell that a couple different ways. If I didn't tell you the symbol, could you still figure that out?
Yeah.
Number of protons, right? So the only two that have the same number of protons are the top two. They have different number of neutrons, which means their mass number is different. Could you tell me which one of these two isotopes is more abundant? How, Joey? Okay, which one is closer?
59.
So cobalt has a weighted atomic average of 58.9332. So there are much more cobalt 59. It might almost be exclusively cobalt 59. The mass defect is there, so we can see it's slightly below 59. But there'd have to be very, very, very few cobalt 61s. All right. What about which one of these has more protons? 1 mole of that cobalt isotope that is most prevalent, or 6 moles of beryllium-9? Or do they have the same? I'm letting this go to 60 seconds, so I'll give you 45 more seconds. This should not be a complicated calculation. All right, a couple more seconds. I think that's actually pretty much everybody. Mohammed, can you explain how you answer this question?
So there's 27 photons basically in A.
Say again?
27 photons.
27 individual protons, that's it? That's every cobalt.
Yeah.
59 has 27. Do we only have one cobalt?
Yeah, okay. You said what?
Do we only have one cobalt?
You have 1 mole of it.
So how many protons do we have?
27.
1 mole.
Times 27.
Correct. So we have 27 moles of protons. Not 27 protons, there are 27 moles of protons.
Okay.
Great. Okay? And then how many do we have in the beryllium sample?
So I just multiplied 6 times 4.
Okay, because?
Because for every mole, for every mole there's 4 protons, and there's 6 moles.
Great. For every mole of beryllium, there's 4 moles of protons. And we have 6 moles, so that would be a total of 24 moles versus 27 moles of protons. Okay? So we're thinking about what's actually included within the sample. And so the one that has 27 moles is more than 24 moles. All right, let's take that and expand upon it a little bit. Which one of these samples has the most atoms? And I would argue you can do this all with logic without doing any calculations. You guys have this on your phones, right? I'm going to go out for 1 second. What is the main determining factor for answering this question?
The number of moles, and then you...
If we want to do calculations, we could. It's going to be slower, though. What's the fast way to do this? What's the main concept behind this? Trey?
Ratio of molecular weight to
Yeah. How heavy is each one? If we have a bag full of nuts that weighs 5 grams and a bag full of pencil lead, whatever you call them, then the one that's heavier, if you have the same total mass, the one that's heavier each item, there's going to be less of. So what can we say about the weights? Is scandium heavy or light? It's really heavy, right? So that's 45 grams per mole. Sulfur, 32. Neon, 20. O2,
You're trying to
32, but it doesn't matter if they're bonded together or not. We're talking about the number of individual atoms. And the weight of oxygen is 16. So that means we're going to have more atoms in 15 grams of oxygen. There's one last question that if you guys want to stick around, we can do this one. Should be a quick question. Oops.
No response.
Can you guys identify what element this is in period 2 that has these ionization energies?
I know exactly what that is.
First time you don't blurt it out, come on,
I'm going to miss you guys. Until next semester. All right, so we're in period 2. So it has to be something in period 2, right?
Yeah.
How many valence electrons? Remember, this is always the way to answer this question. How many valence electrons does this element have? Just showing 8 of the electrons being pulled away, it could show 9, 10, 11, 12. Doesn't matter. How many valence electrons does it have? Pull away the first electron. Pull away the second electron. Is it a big jump yet?
No.
Third electron.
Nope.
Fourth.
Nope.
Fifth.
Nope.
Sixth.
Nope.
When we pull the 7th electron away, that required a lot more energy. So how many valence electrons does this have? Is the 6th the valence still a valence electron? Is the 7th still a valence electron?
The 6th is the valence electron.
So these are all valence electrons. They come off somewhat more easily. This is pulling from the core. This is a much more difficult electron to pull away. If you go about this other ways, it's going to be much more challenging. Think about how many electrons come away before you hit the inner core of electrons. That's how I want you to approach this kind of problem. This will be on the ACS final. This will be on my final, this concept.
So that really is
So then that would be, it has 6 valence electrons, period 2, oxygen. All right. Thank you guys for a fantastic semester. Ooh, I was supposed to give you guys a course evaluation today.
Oh, okay. Is it online?